Hello, everyone. Welcome to our channel. Today, we are going to talk about exact controllability of a vibrating string with fixed endpoint. Can a single boundary control stop a vibrating string fixed at one end? We prove it can. Defining exact controllability as studying any initial state in H01L times L20L to rest in time larger than 2L/C with F belongs L20T apply at X equals 0. We are going to use a mild solution in a moment problem inspired by coupled membrane systems. We construct FT as a series to notify initial conditions. The result will show, unlike 2D cases requiring irrationality constraints for coupling, our 1D result relies on wave travel time and endpoint function completeness, offering a simpler condition, which is T larger than 2L/C. Controlling wave equations has been a rich field since the 1970s, with works like Graham and Russell tackling multi-dimensional systems using multiple inputs. Minimal control strategies, as explored in mass studies on coupled membranes, reference 10, and beams, reference 14, inspire a key question. Can one control suffice enough? We investigate this for vibrating string fixed at one end, determining the minimal time for exact controllability via movement problem approach, constructing it with the complex conditions of multi-dimensional systems. Okay, let's see. Consider string from x equals 0 to x equals L. Its motion follows UTTXT minus C square UXXXT equals 0. With boundary conditions, U0T equals FT, ULT equals T, ULT equals 0, and initial conditions, UX0 equals U0X, UTX0 equals V0X, X belong to omega. And C larger than 0 is the wave speed, is also connecting to the string density. Ft belongs to L2, 0T is a control act equals 0, and U0, V0 belongs to X 0 omega times L2 omega, with X0, 1 omega like Sobolev space, restrict all these conditions. We aim to achieve X UXT UTX equals 0 for T larger than 2L/C. And this 1D wave system is, we are coupling the 2D system, okay? We see which the result will be different. So here we define some space, like the Hilbert space L2 omega with inner product, like UVH is integrate 0 from 0 to L UX VX dx. and U times V. V is H01 omega is the surface space, V is L2 omega, then U is embedded in V densely and continuously. Then from this work, we can define the exact controllability. The system 102 is exact controllable in U times V at time larger than 0 if for every initial day U0, V0 belongs to U times V, there exists a control F belongs L to T such that solution, of course the solution is the one system, the system 1, 2 satisfies the 6, which is to the left, UXT equals 0, UTXT equals 0, okay? X belongs to omega 0, L. Usually we only focus on no controllability, but non-controllability this imply the reachability for any target state in U times V. Okay. Okay. Then from now we define some solution and method for solution. No, solution and the method solution. Okay. Before this, we define the operator A, dA, okay? Then obviously this A is positive self-adjoint in this here with the H, okay? This is F1 value and F1 functions, theta and X, okay? This is also normal basis, okay, for H. Then we introduce system 1011 by UXT equals ZXT plus PXFT, where PX equals 1 minus X over L. Assume F0, FT0 equals 0, We will improve this system the same as system 124. So the solution of the 10 to 11 is the same as the solution of 1 to 4. Then we establish another system which is 12, 13. This system is also the same as 10, 11. We define A, which is the italic A with domain dA equals U times V, and we can improve. This is actually is a semigroup, generally strong continuous semigroup in on V times H. Okay, so then the system 12, 13 so has a solution 15, 15 CET is empty. And this solution is also connecting to 10, 11. The reason to do this is we try to connect, then we know there will be solution for system 1. By this connection bridges, then we know system 104 has a solution, at least has some kind of unique structure solutions, okay? Then we use the giant system, WTT, minus C squared WX equals 0, okay? And without the control part on it. And this is WXT is the solution of this 16, 17. Then we built a mild solution identity. Okay, we build a mild solution by using the calculation technique. Okay, the purpose is to release the control FT to the system 104. Okay, we multiply 2. Remember 2? Okay, it's a U, right? UTTC C square US is 2. Okay, we multiply 2 by the W from 16 to 18. Then we do the integrate over omega and times 0t. And with this calculating, and we will get the 19. We will get 19. We get this 19. We get this 19, then we will be we have the mild solution definition. We say that U and UT belongs to this one is the mild solution of system 1 to 4 if it satisfies 19 or if satisfies 19. Okay. Of course, for any U0, V0 belong to U times V and F belongs to L0 T, with this condition for every W0, 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 W1 belongs to U times V. Okay. Since we have the mild solution of system 104, we target is UXT and UTX equals 0, right? Then if we use this target, we 19 becomes this function equation at 19. 19 becomes this. Then this part is, remember we have WXT, then we put WXT and do one time derivative to the W, and we got WXT, we put X equals 0, then we get this WX0T, this part. This is lambda MT, okay? Okay, then W0 is X this part, WT0 is this part, okay? Then we will have this part, okay? Then we can construct FT. Then we relate to a moment problem before we try to solve the moment problem and try to get FT. So we FT equals F. We use FT equals the series FNT. We try to find whether we can try to find FNT. Okay, in the L202. Remember 19. We put everything into 19. Put everything into 19. And we had this part, we had those part. We put everything in 19. Then we get calculate and comparing. We get a moment condition Cn dash equals this part. Dn dash equals this part. Okay. This part is a moment problem, famous moment problem, okay? Okay, then with this moment problem, we have our main theorem. Our main theorem is assume T larger than 2L/C, and any U0, V0 belong to U times V. Then we say the system 104 is exactly controllable in U times V. Okay, that means we can find the FT, which made U0T, UT0T equals 0. Okay. Okay, we define the density of the sequence as the F value lambda n, and with the density is D, this one, the C pi, L over C pi. Okay, so 2 pi D is 2L over C. Then we, according to well-known result from Graham Russell, we see if T larger than 2 pi D, which is 2L over C, and sequence C dash M, these are Dn dash satisfy this condition, then the moment problem has the solution Fnt belongs to L20T such that this norm on Fn the limit, okay? Thus, then we can have Ft, okay? Then really can find this condition. Actually, we use this part Cn. We calculate Cn is this part, Dn dash is this part, and because the A and B and they are in the L2 omega, which is lead to their bound is the limited boundary, right? So then we can get actually this condition has been fulfilled. Physical condition fulfilled, and all this is we using this result. Finally, we can say this theorem has been verified. Okay, this is our final result, theorem 1. Okay. So it's quite simple. It's comparing the 2D part. The 2D part have found a special set to find the FT. Okay, so 1D part is straightforward. Okay, so that's why we use the moment problem to construct the FT. So final conclusion. A single control FT at x0 put the vibrating string on the rest, exact controllable for t larger than 2L/c. Okay, this which is relating on wave speed and the length. Okay, of course the endpoint functions competitiveness in L2 L, which contribute to the moment problem has a solution for F and T, right? Okay. Okay, all these are reference. Okay, this is the 2D. Okay, exact controllability of a coupled vibrating memory system. Okay, and this is this part of I already talked before, and this next time I'm going to talk the beams. Okay, and coupled beams is also very. This is very complicated. And this one is a simple solution. Just the sample to show the moment problem also can use the 1D solution. Another thing is that we can use HUM on here, but unique mask to solve this same problem, and the answer is exactly the same. Okay, so that's all for today. If you have any question, just put your in the comments. If you want to contact me and know any details, let me know. Okay. Thank you, everyone.